Algebra 1, Investigation 8. We are looking at joint variation in this investigation, which ends up being a combination of direct variation sometimes with multiple variables and sometimes also inverse variation. So joint variation occurs when a quantity varies directly as the product of two or more other quantities. When y varies jointly with a set of variables, y is directly proportional to each variable taken one at a time. For example, if y equals k x z, where k is our constant and it's non-zero, then y varies jointly with x and z. We can also say with this that if I have this equation of y equals kxz, let's plug in, let's say y equals 10xz, then we would say our constant is 10 and y varies jointly with x and z, but we can also say that y varies directly with x and y varies directly with z. Why we say this is that we can still use this relationship of direct variation to say as one increases, it influences the other and it increases as well. So let's look at an example here in that relationship. The equation b equals 3ac is joint variation, which b varies jointly with a and c, and therefore b varies directly with a and b varies directly with c. So the table of values illustrates this relationship between them. So use the table to complete the statements that follow. Doubling a causes b to change by a factor of what? So if I take this a value and I start it at 1 and double it to be 2, what happens with b? Well, 3, if I plug this in the actual equation, b equals 3 with 1 being a and c being 1, we see that b is 3. But if I go ahead and say, you know what, I'm just going to double a and say 3 times 2 times 1, I see that b becomes 6. So b also doubles. So it changes by a factor of 2. Okay? All right, so if I double a, then b changes by a factor of 2 as well. So number 2, doing what to c causes b to change by a factor of 2? Well, let's see what happens. If I take from c and go from 1 and change it to 2, then I see 3 changes to 6. So by doubling c, it changes b to change by a factor of 2. The statements above are true because b is blank proportional to a and b is directly proportional to something. Well, just like I said earlier, the statements above are true because b is directly proportional to a and b is directly proportional to c as well, since we're in joint variation with this relationship. Okay, what if I were to double a, so 1 to 2, and I double c, so 1 to 2, so both of them are doubled. So doubling both a and c causes b to go from 3 to 12. So it causes b to quadruple. So if I multiply this by 2 and this by 2, then it causes b to quadruple. Okay, so let's work with this joint variation with all of this information. So in each case, you must hold one variable constant to calculate changes in the other two variables. If you know y varies jointly with x and z, and also know one set of values, we can use our equation, and this is our general equation for joint variation, y equals kxz, to find the equation of variation. Okay, so suppose y varies jointly with x and z, so we know we're in this situation. Find y when x is 8 and z is 3. We're going to hold on to that information, but kind of table it for a second and really focus on this one set of information that is complete. Y is 20 when x is 5 and z is 2. So number 5, set up an equation in the form of y equals kxz given the values. So I'm going to plug these in and say y is 20. We don't know k, but I do know that x is 5 and z is 2. So what is the value of k? Well, this right side says k times 10, so 20 equals k times 10. Divide each side by 10 and we see that 2 equals k. So what's the value of 2? It equals, or what's the value of k? It equals 2. So use the value of k to write an equation of joint variation. Well, we're going to go back to this, but plug in 2. Y equals 2xz. And now we can actually use this second piece of information to find y. So number 8, find y when x is 8 and z is 3. So I can now use this general form with something missing. So what is y when we have 2 times 8 times 3? Well, 2 times 24 is 48. So y must be 48 in that situation. So we can use full information when we have y, x, and z to find our constant, and then use that constant when we have missing information to kind of fill in the gaps. Okay, now science actually uses relationships like this a lot. So joint variation is found widely in scientific applications. An ideal gas can be characterized by 3 stated values: absolute pressure P, volume V, and absolute temperature T. You can deduce the relationship between them from kinetic theory. This is called the ideal gas law. It's written as pressure times volume equals nRT, okay, where that temperature T we know about. And what we're saying is P is that pressure in atmospheres, V is the volume of the vessel containing N moles, okay, of gas. N moles is the amount of substance, and R is the gas constant. Okay, and we do actually have a constant here. So we can replace R in here to actually have a joint variation situation. We're going to be using, through all of this, that's lots of information, to get down to the fact that we are using the equation PV equals 0.08206 NT. That is our equation that we're going to use. So number 9, what's the constant of variation? Well, that constant of 0.08206 is going to stay the same in each of these situations. So number 10, how many moles of gas does it take to occupy 120 liters of pressure? So 120 liters, so that's my volume. Pressure of 2.3 atmospheres, that's P. And a temperature, that's T, of 340 kelvins. Round the answer to the nearest tenth. Well, just like above, I'm going to plug in what I know. Since I already know our constant, I can just plug in what I know and solve for what I don't. So I start with my PV equals 0.08206 NT, plug in what I know. I know my pressure is 2.3, my volume is 120, so I'm going to multiply those together, equals 0.08206. My moles of gas, N, I don't know what that is, so I'm going to leave it as N. And then we have a temperature of 340. Well, let's simplify each of these sides by saying, well, what is 2.3 times 120? This would be a good use of a calculator here. And we get 276. And then let's simplify the other side. 0.08206 times 340. And we get 27.9004 times N. So the only way that we're going to solve for these moles is by dividing by 27.9004. On both sides, of course. So let's try it. 276 divided by our number gives us 9.89, round to the nearest tenth, so we would say 9.9 moles of gas. Okay, so we would use this to solve for those moles of gas. So that's number 10. Number 11, if a 50 liter container holds 45 moles of gas at a temperature of 473.15 Kelvin, what is the pressure inside of the container? Round to the nearest tenth. Well, in this case, we're missing our pressure. So we have 50 liters as our volume, so I'm going to plug that in using the same equation. We don't know our pressure, but I can say my volume is 50 liters. And then I know that I have my constant 0.08206 times my number of moles. I know that this time. I have 45 times the temperature, 473.15. So I can solve for P in this case. Let's simplify that right side. 0.08206 times the number of moles, 45, times the temperature, 473.15. And I get P times 50 equals 1747.201. And now all I have to do is divide by 50. So I'm going to take that number and divide by 50 so I get P by itself, and I get my pressure at, let's see, rounded to the nearest tenth, 34.9. Let's see, and our pressure is in, let's see, absolute pressure is in atmospheres, so ATM. Okay, so see how we are plugging in these numbers where we know them and solving for the variable that we don't. Lastly, number 12, it says solve the ideal gas law for absolute pressure P. What this is asking us to do is take our original equation PV equals 0.08206 NT, and I just want P by itself. Well, that means that I am going to divide by V on each side and say that pressure equals my constant times moles times my temperature divided by volume. Okay? What we can say with this is a lot of different things. With this joint variation, we can talk about this with direct and inverse variation. So an equation in several variables can be written in terms of one variable, just like we did here. This will produce a quotient of one side of the equal sign in the equation. You can describe variation in terms of joint and inverse variation. So 13, state the ideal gas law solved for P in words using the phrases jointly proportional and inversely proportional to. So when we look at this, my pressure here is jointly proportional to the numerator. So P is jointly proportional to N and T, and P is inversely proportional to the denominator V. So using those words, we would say once again, pressure is jointly proportional to N and T and inversely proportional to V. Okay, so by solving the ideal gas law for absolute pressure P, the equation is written as both joint and inverse variation. Many science applications involve more than one type of variation, as well as the square or square root of variables. So the load P in pounds that a horizontal beam can safely support varies jointly with the product of the width of the beam, W, in feet, and the square of the depth in feet, and inversely with the length L in length L in feet. So number 14 says, with all that information, write an equation relating P, W, D, L, and our constant K. This is how we're going to do it. We're going to take each of these pieces and write them as part of our equation. So the load P varies jointly. So P varies jointly, meaning we're going to have K times a couple variables. And it varies jointly with the product of the width of the beam, W, so that's part of the joint proportion, and the square of the depth in feet. So we have depth, but it's squared. Okay, so P is jointly proportional to W and D squared, and we always have that K as part of it, always there. Lastly, it's inversely proportional to the length in feet, which means it's going to be divided by L, just like we would use inversely proportional. Inverse variation is always dividing by a variable. So that's number 14. This is our equation that we would write. 15 says, how does P change when the length of the beam doubles? Well, let's see. If I had something like this, let's just keep it simple. Let's say W is 1, D is 1, and L is 1. Okay? Well, in this case, I'm going to have P equals K times 1 squared over 1. And I just P equals K. Awesome. But what if we say, you know what, I am going to double the length of the beam. And I now have P equals K times 1 squared over 2, which means that I have P equals K divided by 2. So when I double the length of the beam, just like with inverse variation, if I increase that length, then I decrease the pounds that it can support. Okay, I actually cut it in half. So just like inverse variation, if I increase this amount here, it decreases my other variable. So let's try this again. How does P change when the width and depth of the beam are cut in half? Okay, so let's go back to this here and say instead of doubling that length, let's cut my width and my depth in half. So instead of 1, we have 1/2 for each of these. Well, let's plug it in. K times 1/2 times 1/2 squared divided by 1. When we simplify all that, we see P equals K times, well, that's 1/4 times 1/2, so 1/8. If I'm going to cut the depth of the beam in half, so if I decrease the width and the depth of the beam, then I decrease with this, let me just make sure that I'm saying the correct things. With this, we divide how much it can support by 8. So if I decrease, just like with direct variation, if I decrease those joint variables, then I decrease how much it can hold in the same way. So in this case, if we cut the depth of the beam and the width of the beam in half, we cut the pounds into eighths. Okay? All right. So this is how joint variation and inverse variation work, and there's a few more examples here for you to try. But really it comes back to, do you have joint variation with things multiplied together with their constant, or do you have inverse variation where you divide by your constant? Okay? So I hope this helps with your homework and for studying.